the previous lecture we have discussed about the VSI, that is voltage source inverter, and how we are going to implement the space vector modulation in the VSI, or where we are going to implement the space vector modulation. And in that we have discussed the three-phase VSI as a combination of single-phase VSI, and in that how we are going to apply the space vector. So now we are going to discuss what is space vector modulation. Actually, in the space vector modulation, we are going to represent the voltage vectors as a in the space as a space vector format. So when you are going for the definition, the space vector representation of a three-phase quantities xa of t, xb of t, and xc of t with space distribution of 120 degree apart is given by. Actually, this equation itself having some problems when I was making this. So just write it down. This is x of t, or our space vector representation. It is equal to 2 by 3 into the into means it is a whole square bracket into xa of t plus a xb of t plus a square xc of t. This is the space vector form of three-phase quantities xa of t, xb of t, and xc of t. Here a and a square are: a is equal to e power j 2 pi by 3, a square is equal to e power j 4 pi by 3. If you are going to add these things, 1 a square, then you will be getting 0. This is the concept of that. So already you know all these things, what is a square and all. We have done in the math, or even in power system we have used these quantities. Sometimes you may be used at alpha. 1 plus alpha square is equal to 0. That format you may be remembering. The same thing we are applying here. So actually this a square represents 120 degree phase shift. Okay, here 2 pi by 3, 4 pi by 3. That means it is phase displaced by 2 pi by 3. That is 120 degree. Okay, or you can write e power j 2 pi by 3 as cos 2 pi by 3 plus j sin 2 pi by 3. This is pure mathematics, and this is also cos 4 pi by 3 plus j sin 4 pi by 3. X can be a voltage, current, flux, and does not necessarily has to be sinusoidal. This is that means it is a equation for any three-phase quantities like voltage, current, or flux. And in this condition, it is you can say that it may not be sinusoidal also. Okay, so this is a space vector equation. Actually, some equation having some problems, technical problems. Anyway, whatever I told here, the same thing will be repeated everywhere. So when you are representing a three-phase sinusoidal voltage, you can say this is the R phase, this is your B phase, and instead of Y phase, we are writing G phase. Or you can say A, B, and C. We are using here A, B, C as a terms. So this red line is the VA of T, and VB of T, and VC of T. These are the three-phase sinusoidal voltage, and if you are going here, I said here we have represented with X, XA, XB, and XC. Instead of that, we are going for the voltage representation. So we are going to represent it in the voltage vector format. Here you can see instead of x it is v, and xa instead of xa it is va, xb it is vb, and xc it is vc. All other is this thing. Again I will repeat this. V is equal to 2 by 3 into whole, like here whole bracket is the 2 by 3 into va of t plus a vb of t plus a square vc of t. uh, this is because of I think font problems. I don't know why it is coming like this. Let it be like that, but you keep it in mind that it is 2 by 3 into va of t plus a vb of t plus a square vc of t. Instead of x we are substituting that with the voltage vector. So v va vb vc, and if you are considering one line here, or wherever, if you are considering at here at t is equal to t1, omega t is equal to 3 by 5 pi. 3 by 5 pi means if you are considering the whole signal strength as 2 pi, then 3 pi 3 by 5 pi means this is the pi, 1 2 3 4 5, you can say that here 5 divisions are there. So 3 by 5 pi means this point, and if you are considering this, each voltage vector will be having certain value. So if you are finding that value, you say that va is equal to 0.9511 vm, here 9511 vm, and here it is minus 0.208 vm, and here it is minus 0.743 vm. If you add all these things with the phase vector formulation, you will be getting the v. So if you are okay, va vb vc we have given. This is also negative. I don't remember what I have said. It is minus 0.743 vm. It is vm is the maximum value of voltage. And you can say that we can represent all these quantities with this vector, like v a total v is equal to uh, this is va vb and vc. When you are considering the vectors, like va is positive and its magnitude is 0.9511, 0.9511, we are taking 0.9511. And vb actually this is the vb, and it is magnitude is minus 0.2048. So it is minus means opposite to this, and 0.208 times the length of the va, or the magnitude vm. It is a 0.9511 times of vm. Here it is minus 0.208 times of vm, and this is the vc, so it is minus 0.743 times of vm. So if you are adding all those things, actually this is an approximate diagram. When you will be thinking like this is not 0.743, let it be like that. Think like it is not exact figure. Anyway, it is necessary for thinking like that, or to describe all those things. So this is va, and this is vb, and this is vc. So you will be getting the whole added together, then you will be getting the getting v. Okay. uh, So this is actually the vector formulation. The space vector, actually this is the space vector. You will be having va vb. This is a va axis or a axis. This is b axis. This is c axis. Any vector which is in this space, you can represent it with the three axis parameters. Three-phase quantities vary sinusoidally with time. So actually, when you are considering the space vector formulation, this all vectors are rotating synchronously. This is a stationary representation or a at certain time. This is the um, at sometime this is the position of the vector, you can say like that. Or otherwise, if you rotate and if you are having a axis here, a axis here, c axis here, and b axis here, this is the same space vector which is showing. According to that, all the other vectors will move, and the same magnitude and phase angle you will be getting, and this phase angle will be considered with respect to a axis. uh, so three phase quantities are sinusoidally time varying with frequency f. When this frequency f is changing, then the speed of the rotation will be changing. Anyway, we are not considering the speed of rotation. Here the space vector rotates at 2 pi f, and when the frequency is changing, according to that, the space vector speed it is changing. This is a and its a magnitude is vm. All the space vectors having magnitude vm. So this is the space vector formulation, and we have to discuss about how we can synthesize the sinusoidal voltage using VSI. That we will discuss in the next session.